Any questions so far? Okay, good. So now what we're gonna do is we're gonna do hypothesis testing on this very same situation, but we're gonna do it precisely with all the formal steps. And you'll see that basically it's similar to this intuition that we just talked about. So let's go ahead and do hypothesis testing formally. So this will be formal steps. So the first step of hypothesis testing is we want to identify two statements. One statement is called the null hypothesis. And the other statement is called the alternative hypothesis. Each one has its own mathematical abbreviation or symbol. The null hypothesis is abbreviated as capital H with a right subscript of 0. And the alternative hypothesis is identified as capital H with a right subscript of 1. So H0 versus H1. Or this 0 often looks so much like an O that people also use HO instead of H0. And because a 0 or an O is often read as not, this is read as H naught as well. So H0 or H naught. And the alternative hypothesis, being H1, can also be represented as HA for alternative. Okay, so now let's talk about how to actually identify these statements. So if you look at the original claim here, that the coin is unfair, there's always a second statement that can be made, which basically represents the opposite. So every statement has an opposite statement to it. So what would the opposite of the coin being fair, unfair be? Coin being fair, okay. And so that opposite statement, formally we can call that a counterclaim. So the opposite statement or the counterclaim would be the coin is fair. So of these two statements, one will be the alternative hypothesis and one will be the null hypothesis. Right now, we just don't know which is which yet. So let's talk about identifying which is which. So of these statements in English, the next step would be to convert them into mathematical notation. So let's say we start with this statement, the coin is fair. So this symbol we've seen before. This represents the proportion of success for the population. So let's say success here means flipping heads. So P would be the probability of flipping heads. So what would this symbol equal if the coin were actually fair?
1/2.
Yeah, 1/2. So notice that this P is the population variable, not the sample variable that has a hat. So this is the population proportion of success for a fair coin, would end up being 0.5. So if the coin were really fair, then in the long run, the proportion of heads is going to be 0.5. And so what about the other statement? If the coin is unfair, what should the proportion of heads be? Could be 0.9. It could be 0.9, but what else could it be?
Above or below.
Yeah, very good. It can be anything as long as it's not 0.5. It can be 0.9, it can be 0.2, it can be 0.8, and so on. Right, so P can be anything as long as it's not 0.5 if the coin is unfair. So So another way of saying P does not equal 0.5 is to say that either P is greater than 0.5 or P is less than 0.5. Okay, so now that we have the two statements, now we're ready to identify the null hypothesis. And so the null hypothesis will always be the statement that contains equality, or the equal sign here. So P equals 0.5 here represents the null hypothesis. So it's going to be HO or H naught or H0. And the other statement that remains automatically will be the alternative hypothesis. So that'll be H1 or HA. Any questions? Okay, so next step, once we identified HO and H1 in our problem, step 2 is to assume that HO is true. And because this step involves assuming, you're actually not physically doing anything in this step, but it's actually the most important step because it's setting the foundation for everything else that's coming. So we're assuming that HO is actually true. And so in this example, what is it that we're assuming to be true? Yeah, you're assuming that the coin is fair because that's HO, that's a null hypothesis. So in this example, i.e., assume the coin is fair, or mathematically, P really does equal 0.5. Okay, so one way that we can visualize this assumption is through a distribution that we've talked about before. So let's say that we look at the distribution. And let's say, again, on the x-axis here, we're going to look at the number of successes out of the number of trials. So in this example, success is getting heads, and the number of trials is 100 flips. So we're going to look at the number of heads out of 100 flips. And if this assumption is actually true, and the coin is actually fair, and the true proportion of heads is actually 50%, then if we flip this coin 100 times, how many heads should we expect to observe with the greatest likelihood?
50.
Yeah, 50. So at 50, we have a bar with a certain height that represents the probability of observing that many heads out of 100 flips. So even if this were true and the coin were perfectly fair, should you expect to observe 50 heads every time you flip it 100 times? No. Okay. So you very well could observe 51 heads, but the probability of that is a little bit less than it was before, so the height of this bar is a little bit less. So as you move away from 50 in either direction, the height of this bar, or the probability, will get a little bit less. Same thing in the other direction. Okay, so this is the distribution or the visualization of this assumption that the coin is actually fair. And so if you flip it 100 times, you should see a probability distribution representing the number of heads you actually observe out of 100 flips. And so we've seen this before. This is a binomial probability distribution because the heights of each of these bars, or the probabilities, are probabilities of a number of successes out of another number of trials. So all these probabilities are binomial probabilities. So this is a binomial probability distribution. And we said that because we recognize that, it's very easy to find the mean and standard deviation of this binomial probability distribution. And what would that be? The mean is where we said this peak was in the probability, and the peak occurs at 50, so we know the mean is 50. But in this situation, it's kind of intuitive that the mean is 50, but how would we calculate the same number? What formula would we use? Yeah. Well, that's the standard deviation. Let's do the mean first. NP. Very good. So this is n times p, which is 100 times p is 0.5, because we're assuming the null hypothesis is true and p really does equal 0.5. So the mean is 50. And the standard deviation is the square root of NPQ, or the square root of n is 100, p is 0.5, and if p is 0.5, q is also 0.5, because q is the complement of p. So if you evaluate this, you'll see that the standard deviation, or the square root of NPQ, is 5. Good. Okay. Questions? All right. So this is the visualization of this assumption that the coin is fair, and you're flipping this coin 100 times. So the next step is that you want to ask yourself this question. So you notice that in step 2, you haven't involved the observation yet. So you haven't involved the fact that you observed 55 heads, or that you have observed 90 heads for the second coin. But now in step 3, we're going to involve the observation. And we're going to ask ourselves, is the observation consistent with this idea that HO is true? So is the observation consistent with the idea that HO is true? And basically, this is a yes or no question that you can either answer one of 2 ways. So let's now talk about how we can answer this yes or no question as to whether this observation is consistent with this idea that HO is true. So this idea that HO is true is basically represented by this picture. This is HO being true. So if we have an observation, how do we determine whether that observation is consistent with the distribution or not? How do you think we can do it? For example, if we had a value in a distribution, like a certain IQ score in a distribution, how do you determine whether that IQ score is consistent or typical for that distribution? Yeah.
Z-score.
Yeah, very good. So Z-score, and then anybody want to follow up with that? Okay, so, yeah.
If the Z-score is small, then it's more typical. If it's large, then it's less typical.
Okay, excellent. So if the Z-score is small, that means it's close to the mean. That means it's typical. And if the Z-score is too large, that means it's far away from the mean, and it's not typical for this distribution. Very good. So remember, even in confidence levels, any conclusion we made had, even in confidence intervals, any conclusion we made had a certain confidence level associated with it. So let's say that we want to make a conclusion that we are, let's say, 95% confident about it. So let's say the confidence level is 95%. So we've been saying that the area around the mean under the bell curve, we've been designating as the confidence level. So same thing in this example. Our confidence level will be visually this area under this bell curve, because even though technically this is a binomial probability distribution, we can approximate it with a bell curve. And basically the area around the mean under the bell curve, or this middle area around the bell curve, that's the confidence level here, the 95%. And this middle area here is being separated out by these two boundaries. And we have this area here that is either less than the boundary or greater than the other boundary, which we designate as the extreme values of the distribution. So this left shaded area are values that are considered too low, and these values on the right are considered too high for the distribution. And these shaded areas we call the tails. So on the right side, we can call it the right tail, and on the left side, it's the left tail. And just so we can refer to it easily, any region that's not the tail, we can call the body of the distribution. So basically, we've been saying that any value that is close to the mean or not in the tails, we can consider as being typical or consistent for that distribution. In other words, any value that is in the body of the distribution, we can say is consistent or typical for that distribution. And any value that is in the tail, either the left tail or the right tail, can be considered as not being typical for that distribution. Okay, so basically, to answer this problem, this question of whether the observation is consistent with that distribution, then it just boils down to, is the observation in the body or the tail? So if the observation is in the body of the distribution, then we can answer this question as yes, the observation is consistent. And if the observation is in the tail of the distribution, then we can answer this question as no, the observation is not consistent with this distribution. Okay, so now let's go ahead and incorporate this observation of 55 heads. So right now we don't know whether it's in the body or the tail, but let's say, to start, we're just gonna guess. That, let's say that it's somewhere close to the tail, but let's say it's still in the body at 55. And if we're wrong in this guess, then we can change it later. But how do we know for sure whether this observation is close enough to the mean of 50 to be considered in the body of the distribution? How do we quantify whether the observation is considered close enough to the mean or not to be in the body?
Generally, we go by 2 standard deviations from the mean.
Yeah, very good. So generally, in the previous homework questions, you've seen that you go by, if it's within 2 standard deviations of the mean, then you consider it to be close enough to the mean. But now, you're ready to know that that 2 standard deviations is really just an approximation that now you'll say, based on this confidence level of 95%. So if the confidence level changes, then that number 2 might be a different number. So now, let's go ahead and, so basically there's this boundary here that designates where the tail actually starts. And that boundary is gonna have its own z-score. And that z-score is called the critical z-score. So this boundary, defining where the tail starts, will have a z-score called the critical z-score. So how do you think you can find that critical z-score?
Is the table?
Yeah, use the table, very good. And the table has a relationship between two quantities, z-score and area to the left of that z-score. If you know one, you can find the other. So if you're trying to find this z-score, if you know the area to the left of that, under the bell curve, then you can easily find that z-score. So what is the total area to the left of this z-critical that we're trying to find?
0.975.
Very good. So the 95% in the middle plus the left tail of being 5% divided by 2. Because 95 in the middle means that now you have 5% left over, and 5% divided by 2 is 2.5%. So the total area to the left of the z-score that you're trying to find under the bell curve is 97.5%, or 0.975. So we want to go to the z-score chart and look up 0.975. Yep. What z-score are we doing?
It's 1.96.
1.96. So if this z-critical of where the right tail starts is 1.96, what do you think the other z-score of where the left tail starts is?
Negative 1.96.
Yeah, very good, because this bell curve is symmetric. So it's gonna be the same z-score value, but just a different sign. So it'll be negative 1.96. So that means that all the values that are considered in the body of this distribution are between negative 1.96 and positive 1.96 for a z-score. In other words, they're all values within 1.96 standard deviations of the mean. So now you're ready to know that that 1.96 was an approximation of the two that you've been using throughout the class. And that's based on 95% confidence. Now, if the confidence level changed, then the z-score of where the critical values started would be different. So these z-scores again are based on the given confidence level. And for 95% confidence, the z-score is plus or minus 1.96. But if the confidence level changed, then these z-scores would also change. Any questions so far? Okay, so now that we know where the tails actually start and where the critical z-scores are by using the table, how do we determine whether this data point of 55 is considered inside the tails or the body of the distribution?
You need to find the actual point that begins the tail.
Yeah, the point that actually begins the tail is that z-critical that we found, 1.96.
Well, the value that represents.
Yeah, very good. So this data point of 55 will have its own z-score, and we're going to find the z-score of this data point, and we call that the test z-score, or z-test. So the test z-score is the same way that we found the z-score throughout the semester, which is the number of standard deviations that data point is from the mean, which is x minus the mean, divided by the standard deviation. So the test z-score here will be x minus, because this mean is found from this formula of n times p, you can just replace that with np. And the standard deviation for this binomial distribution is found from the square root of np cubed. So you can use that formula. So now we're just substituting in numbers. X is going to be the data point itself, which is 55. Minus the mean found from NP, which ends up being 50 for a fair coin. And then divided by the standard deviation, which we calculated together to be this 5 from the square root of NPQ, the formula. So if you evaluate this, you're going to get 5 on top divided by 5, which is 1. So that means that this data point has a z-score of 1, or z-test here is 1. So this is z test equal to 1. So now that we know that our test data point has a z-score of 1, and the tails start at 1.96, and negative 1.96 on the other side, then now how do we determine whether the observation's in the body or the tail?
You make sure that the z-test score is somewhere between the mean and the associated tail that you're looking at.
Yeah, very good. So all this is saying is that our z critical of 1.96 means that the right tail starts at 1.96, and everything to the right of that is in the right tail. And likewise, our left tail starts at negative 1.96, and everything to the left of that is in the left tail. And if you're not in either tail, then you're in the body of the distribution. So our observation has a z-score of 1. That means it's neither in the right tail or in the left tail, so it's in the body of the distribution. Okay, any questions? So now that we compare those two numbers, z-test and z-critical, now we determine that the observation is in the body of the distribution, not in the tails. So now we're ready to answer this question in step 3. So because the observation is in the body of the distribution, we answer this question as the observation is consistent. So yes, it is consistent with the idea that HO is true. So now we're ready to formalize the actual conclusion itself. So it turns out that this part, the actual formalizing in words of the conclusion, turns out to be the most confusing part of hypothesis testing. And this is the part that confuses students the most. And because it confuses students so much, they usually just memorize the conclusion. And the issue with that is that you'll see that the wording in this conclusion seems like it's overly technical. And it seems like there's a lot more words than necessary. But if you just memorize it, then if it changes just by a little bit, you won't be able to understand whether the new wording is actually the same as the one before. So we really need to understand this and not just memorize it. And so instead of just giving it to you right now, we're going to build up to it. So this step here is basically answering this question of, we have an observation here, and we want to know whether it's consistent with some idea. So basically, we're just comparing two things, an observation and an idea, and seeing whether they're consistent with each other. And based on that, if they're consistent, we reach one set of conclusions. If they're not consistent, we reach another set of conclusions. So let's say, so instead of having our idea be this complicated thing, being the null hypothesis, let's make our idea something very simple so we can extract out the most important things here. Let's say that in this case, our idea is that all sheep in the world are white. So all sheep are white. And let's say that our observation to try to test the idea is that we select 100 sheep from all over the world. And let's say of the 100 sheep we observed, we noticed that all 100 of them happen to be white. So in this example, is the observation consistent with the idea?
Yes.
Yes. So in this example, the observation is consistent with the idea. And so the question is, now what can you say about the idea? Can you accept the idea that all sheep in the world are white just because you have this one observation that is consistent with the idea?
No.
Yeah, very good. So we do not just want to accept the observation, accept the idea, because this idea has to do with all sheep in the world, and we've only observed a much smaller sample. So we can't just accept this idea. But the best we can do is not throw out the idea yet. We should continue to hold on to the idea that maybe all sheep in the world are white and continue to observe more sheep. So the best thing we can do again is not toss out the idea. So another way to say that is do not reject the idea or fail to reject the idea. So again, what that means is that we don't want to throw out the idea. Don't discard the idea yet. So that's what fail to reject means. But when we say fail to reject the idea, it doesn't mean we can never reject the idea in the future. It just means for now, based on this observation of 100 sheep, we're not going to yet reject the idea. So another way to say that is that there's not enough evidence now to reject the idea. But maybe later on, there might be evidence enough to reject the idea. So another way to say that is that there is insufficient evidence to reject the idea. So in this example, if we observe a small sample that is consistent with our idea, we can't just go ahead and accept the idea. The best we can do is not throw out the idea or not reject the idea yet. So another way of saying that is that there's not enough evidence yet to reject the idea.
And mostly because of the sample size itself, since it's so small?
Yeah, that's part of it. And even if the sample size were large, let's say that you gather 1 million sheep, but there's still more sheep in the world than 1 million sheep, then can you accept the idea in that case?
So can you ever accept the idea?
Yeah, that's the question. Can you ever accept the idea? And what's the answer to that?
Maybe.
So if you've observed every single sheep, and every single sheep is white, then you can accept the idea that every single sheep is white because you've observed them all. Right? But in this case, because you've only observed a smaller sample, then you've only proved your idea for that limited number of observations. And so if you wanted to prove that your idea is true, you have to show that it's true for all possible cases. And so in this case, we've only observed a small sample and not all of them.
So would the answer be something like within our observations the idea is true?
What is it now?
So would it be something like within our observations the idea is true?
That's one way of saying it. But again, we want to make our conclusion about the entire population and not just our sample. Okay, good. So this is if we have a sample that is consistent with the idea. Let's say now we have an observation that is not consistent with the idea. So let's say that we happen to select, let's say now 104 sheep. And of those we see that 3 are gray and 4 are black sheep. So is this observation consistent with the idea that all sheep are white? No. So now we have an observation that is not consistent with the idea. So now what can we say about the idea being true? The idea that all sheep are white?
You can't reject it.
So again, our idea is the same, which is all sheep are white. And in our sample, assuming it's a good sample, we've already observed that something inconsistent with the idea. So what can we say about this idea that all sheep in the world are white?
It's false.
Yeah, so all sheep in the world can't possibly be white because already we observed something different. So now we can go ahead and reject the idea. So you notice that we have a very strong conclusion here. Rejecting the idea is very definitive. So this means that you can have this definitive conclusion with just this one observation. You don't need any more observations. We're done. We can reach a strong conclusion now. So another way of saying that is that there's enough evidence to reject the idea. So another way of saying this is that there is enough or sufficient evidence to reject the idea. So, in this case, you have a very strong conclusion. You're able to reject the idea. You don't need to observe any more things. You're done. Versus previously, when we had an observation that was consistent with our idea, we said that we were unable to make a strong conclusion, and the best we can say that we definitely cannot just accept the idea, but the best we can do is fail to reject the idea and not throw the idea out. And the best we can say is that there's not enough evidence yet to reject the idea. So, in one case, if the observation is consistent with the idea, we make a weak conclusion. If the evidence supports the idea, then we're able to make, if the evidence does not support the idea, if it's inconsistent with the idea, then we can make a very strong conclusion. So, why is there that difference? Why can we make a strong conclusion if it's not consistent, but why can we only make a weak conclusion if it is consistent?
Because of it being a sample of the entire population and the thing that you're trying to prove being so black or white of an answer, as soon as you find something that doesn't match it, it's incorrect. Because you have yet to sample the entire population of sheep with the example that you still found all of them white, you couldn't determine it to be incorrect.
Okay, excellent. So if you want to show that an idea is true, you have to be able to show it that it's true for all possible cases. And from the nature of what we're doing, we're only observing a small sample, so we're not able to show that it's true for all cases. So we can't prove that the idea is true. So if you want to prove an idea is true, you have to show it for all possible cases. And if you can't, then you can't make a strong conclusion about whether the idea is true. But if you want to show that an idea is false, it's much easier to do that. And to show that an idea is false, all you need is one counterexample. And that's what we're seeing here, is that one counterexample, that one counter-observation is enough to show that the idea is false, and we're able to easily reject the idea. Any questions? Okay, so that's with the simple example of this sheep example, but this example generalizes to what we've been doing before, which is if the idea happens to be now HO, or the null hypothesis. So now let's go back to that. So previously then, we had 55 heads, which we showed was in the body of the distribution, because we compared z-test to z-critical, is in the body of the distribution. And so because of that, we have this observation that is consistent with the idea that HO is true and HO is being a fair coin. So if 55 heads is consistent with the coin being fair, then what can we say about the idea? Can we accept the idea? No, we cannot accept the idea because we have one observation, 55 heads, that is consistent with this idea that the coin is fair, so we can't just accept that the coin is fair. Just like with the sheep example. We can't accept the idea. But the best we can do is fail to reject the idea, or say equivalently that there is not enough evidence to reject this idea that the coin is fair. So another way to say that is if the observation is consistent with the idea of HO being true, the best we can do is fail to reject the idea, and the idea under consideration here is HO being true. So we fail to reject HO. So in this example, HO is the coin being fair. And so basically we're saying we're not gonna reject the idea that the coin is fair. So that's another way of saying that is that the coin could still be fair. We're not gonna reject that notion.
For the homework of this, are you gonna expect us to like type this out, or is it gonna be like a drop down menu of like?
It'll likely be drop down menu or multiple choice, we pick the correct phrase. And that's why you need to understand this, because the multiple choice or the phrasing that's presented to you might be slightly different. And if you understand it, then you'll be able to know whether that variation is still considered correct. Any other questions? Okay, so the conclusion here is that we're gonna fail to reject HO. And vice versa, if our observation, instead of 55 heads, had been 90 heads, then do you think the observation was gonna be in the body or the tail of the distribution?
Tail.
Yeah, it's gonna be in the tail because it's gonna be very far away from this mean of 50, and we can quantify that by finding the z-score of that data point. So if we had plugged in 90 in here, we would have gotten 90 minus the mean of 50 divided by the standard deviation of 5, so that would have been 40 divided by 5, which is 8. So the z-score of the observed data point would have been 8, and 8 is a very large number of standard deviations from the mean, so it's very far right, and it's definitely going to be to the right of where the tail starts, which is at 1.96. So if the observation had been 90, then the observation would definitely have been in the tail. So in that case, if we go to answer this question, is the observation consistent with the idea that HO is true? If it's in the tail, then the answer to that question will be no. So if we have an observation that is not consistent with the idea, what can we say about the idea being true?
It is false.
You can reject the idea. Very good. So over here, you can reject the idea. In this case, the idea is HO. So you can reject HO. And again, that's a very strong conclusion. So these are the correct conclusions, but they're phrased in terms of HO. But remember, HO is manufactured. That's from the first step here, that we manufactured HO and H1. So you always want to bring the conclusion back to the original claim. So in this case, was the claim H1 or HO?
H1.
Yeah, the claim was H1 based on the first step of hypothesis testing. So our conclusion here is in terms of HO, not H1. So now we want to formulate an equivalent conclusion, but in terms of H1. So let's do the easier one first. So if we're able to reject HO, what can we say about H1?
H1 is true.
Yeah, there's only two possibilities here. The coin is fair or not fair. There's only two ideas. And if you're able to reject one of the ideas, then that means that you can outrightly accept the other idea. So if you can reject HO, that means you can accept H1.
That's if it was 90 though.
Yeah, that's if the observation were the tail, like if it were 90 heads. But now, let's go back to the other case. So if you fail to reject HO, that means that what you can say about H1 is that the opposite of fail to reject happens to be fail to accept. So if you fail to reject HO, that means you fail to accept H1.
So in our case, the second coin of 90 was it just happened to be 90.
Yeah, that's actually what we actually observed. We observed 90 heads when we flipped the coin 100 times. So that's what you actually observed. So in the second coin, we're just saying, for sake of example, if we had flipped the second coin 100 times and we observed 90 heads, then we have the situation where we're able to conclude that the coin is not fair. Okay, so in the example where we observe 55 heads, and the observation happens to be in the body of the distribution, then the conclusion we end up making is that we fail to reject HO, and equivalently, we fail to accept H1. So, and because our claim is H1, we end up saying we fail to accept the claim. So that ends up being our final conclusion. And so, again, this wording is very confusing to students, especially when they first see this. So let me talk more about what it means to fail to reject or fail to accept. So you can think about where you stand regarding these ideas on the spectrum. So on the spectrum, you either reject the idea or you accept it. But also it's possible to be anywhere on the spectrum as well. It's not just this one or the other. So you can be anywhere along the spectrum. And so when we say that we fail to reject HO, for example, so I'll go ahead, I'll just say reject the idea or accept the idea. So when we say we fail to reject, that means that our position can actually be anywhere along the spectrum. The only one that we're excluding is this rejecting. So we're not gonna reject the idea, but everything else is possible. So this is why rejecting an idea is not the same thing, or fail to reject the idea is not the same thing as accepting. Because any one of these other positions along the spectrum is still possible. So not rejecting the idea is not the same thing as flatly accepting the idea. Right? And vice versa, if you fail to accept the idea, so if you fail to accept, that just means that this one possibility is not being considered, but everything else is still possible. So when we say fail to accept, that doesn't mean reject, but you can think about it as maybe being a little bit closer to rejecting than accepting. And likewise, failing to reject doesn't mean accept, but maybe you can think of it as being a little bit closer to accepting than rejecting. Okay. Any questions? Okay. So basically that's hypothesis testing formally, and you see that even though the final conclusions is stated in a way that's much more rigorous than before, the general idea is exactly the same as when we talked about this intuitively. So at the end, again, with any hypothesis testing, we have a claim about the population we're trying to test. In this case, the entire population of coin flips is unfair, which means that it's not 50%. And so we have an observation to try to test the claim. In one case, we observed 55 heads. In a second case, we observed 90 heads for a different coin. And then what we did was we compared the observation to this model. And the model before, we called it a model, but now you're ready to know that the model is what? It's the null hypothesis. So this null hypothesis that we identified is this model that we're comparing with the observation. So the null hypothesis, when we identified it, we chose the statement that contained equality to be our null hypothesis. So here, the statement that contains equality is that P equals 0.5. So that coincides with the coin being fair. So again, the null hypothesis is the statement that has the equal sign so that we can latch on to a number to build a model around. So that's what we did here, is we latched on to this, this p equals 0.5, so that we had an equation that was equal to one number, so that we could latch onto that and build a model around it. So that's what we did. We compared this observation to this model, and now you know the model is the same as the null hypothesis. So I'll write that. So that's HO for the null hypothesis. So if the observation was close to the model, then we said that maybe the model was true, and in this case, maybe the coin was fair. And so that's really what we were saying formally, is that if the observation was close to the null hypothesis, which means that it's in the body of the distribution, then we don't throw out the idea that the null hypothesis is true. So that's what this is saying. We don't reject the idea that the null hypothesis is true. So that means that maybe the model is true, maybe the null hypothesis is true, and maybe the coin is fair. So that's all that this formal language is saying. It's consistent with this intuition that we said earlier. And vice versa, if the observation ends up being 90 heads, and we compare that to the model or the null hypothesis, we see that the observation is too far away from the model, and intuitively we said that the model could not possibly be true. It could not possibly have generated this observation. And so formally what we did was, again, we asked if the observation was consistent with the model, meaning that is it close to the model? And if we say no, that means it's in the tail and it's not close to the model. And in that case, we reject the model or reject the null hypothesis. That's exactly what we did over here, is we're able to say that we rejected the model and said that the model is not true. So both perspectives you should see are consistent to each other. The informal perspective versus the formal steps are all consistent with each other. Any questions? Okay. So there's some subtleties here that I want to bring to your attention. So one thing that we did was to decide whether the observation was in the body or the tail. We did that by comparing two z-scores. By comparing z-critical, which is where the tail started, to z-test. Z-critical always comes from a table. Z-test will always come from a formula. So the formula that we used was this formula, where we took the data point minus the mean divided by the standard deviation. And the mean was NP, the standard deviation was the square root of NPQ. It turns out that the formula that is in your book and the instructions on the software present to you will be a different formula, but it'll be the same answer. And so let's talk about that to avoid confusion when you're doing the homework. So this z-test, we'll say, is the formula that's presented in class, but the one in your book will look different, but you're going to get the same answer, but it just looks different. So in your book, your z-test will be this formula. So this is p hat minus p divided by the square root of pq divided by n. So I think the formula we talked about in class is simpler to use, and it also makes more sense based on what we've already talked about throughout the semester. It's consistent with what we've talked about. So that's why we talk about this formula in class. But let's talk about this formula that the book suggests you use. You'll get the same answer. And we'll talk about substituting the numbers so that you're free to use which of the two formulas you want. So P hat here is gonna be the proportion of success in the sample. So in our example here, our sample was that we observed 55 heads out of 100 flips. So what is P hat, or the proportion of success in that sample?
55 over 100.
It's okay. Yeah, so it's gonna be this 55 divided by 100, or 55%, good. Right now, I'll just say 55 divided by 100, so you know where the numbers came from. And then what is P gonna be? So P without the hat, remember, is the proportion of success, but in the population. And we technically don't know what that is. We don't know out of the entire population of coin flips for this particular coin what the true proportion of success or percentage of heads actually is. But there's a step in hypothesis testing, the second step, where you assume that HO is true. And HO is that it has to do with the population measurement, and you're assuming that the true value of P is equal to 0.5. So that's what we're gonna use here. We're gonna use 0.5 as being P, because we're assuming that the coin is fair and P is 0.5. And then we're gonna divide by this quantity, the square root of PQ over N. P again is gonna be the same 0.5. Q will be the complement of that, or 1 minus now P, which turns out here to be 0.5 as well. And then N is the sample size, or the number of times you flip this coin. In this case, 100. So it turns out to be 0.5 times 0.5 divided by 100. So if you punch this in your calculator, go ahead and let us know what you get. Yeah, you're gonna get exactly 1. And this is the same z-score that we got by using this in-class formula. So if you change this back to 55, you'll see that the z-score again is 1. So it turns out that this is not a coincidence that you get the same answer with both formulas. And the reason it's not a coincidence is because if you look at the actual numbers that were plugged in here, if you look at just the first number, in the new formula, we use 55 divided by 100, but in the old formula, we use 55. So that's just a difference of dividing by 100. So going from the old formula in class, the new formula in the book, we just divided by an extra 100, right? And then if you look at the second term, what's the difference between going from 50 to 0.5? How do you go from 50 to 0.5? What would you have to do? Divide by 100. So each of these terms on top are dividing by 100 to get from the first formula to the second. And it turns out that the bottom term, if you do a little bit of algebra, you'll see that to go from the square root of NPQ to the square root of PQ over N requires dividing by N. To go from the square root of NPQ, you divide by N to get the square root of PQ over N. So basically, each of these terms, we're dividing by the same constant number. And because of that, we're basically just multiplying by 1 and not changing the value. So that's why both these formulas are the same, but they look different. And you can use any formula. I just happen to think that first formula is easier to teach and easier to use, but you're free to use any one of them. Okay, any questions? Okay, so the next important subtlety is that this part of the visualization here, you notice that there are 2 tails that are drawn in the picture. So in this example, it turned out that this was correct because we have a 2-tail hypothesis test. What that means is that anything that is not the confidence level of 95% gets distributed across two tails. So the remaining 5% here is distributed across two tails in the distribution. So this is called a two-tail test. And by the way, the amount of, so here the confidence level was given to us as 95%. And in the past, the amount of non-confidence, do you remember what that's called, the symbol that's used? So the amount of non-confidence here is 5%. And in the past, what do we call that?
Alpha.
Yeah, that was alpha, excellent. So the alpha is always 1 minus the confidence level. So here, alpha is gonna be the 5%. So when we have a two-tail test, that amount of alpha is gonna be divided across two tails. And that's why we have 2.5% on each tail. But sometimes we can have a one-tail hypothesis test where this alpha is only on one tail. And so it turns out that the way that you distinguish between the two, whether it's a one-tail test or a two-tail test, it turns out that that's really easy to do. And the way that you do that is you always look at H1. So in our example, after the first step of the hypothesis test, where we identified HO and H1, we said that H1 was this statement here. So then you look at the number of inequalities that are in H1. So in this case, the number of inequalities in H1 is up here. You notice that you have P is either greater than 0.5 or P is less than 0.5. You have two different possibilities for inequalities. So because there's two inequalities here, you have a two-tail test. So later on, we'll see examples where if you look at H1, you'll see only one inequality. For example, you might see P is greater than 0.5 only, and you won't have this other or in there. In that case, this will be a left tail test. And in particular, if you only have this, because P is greater than is to the right on the number line, so this would be a one tail test, and in particular, a right tail test, if you only had this one inequality. But because in this example, you had these two possible inequalities, that was a two-tail test. Okay. Any questions so far? All right, so we only have a few minutes left. There's another concept that's important. So you can start doing your homework, but on your homework, there's a component of the question. So your homework will basically be hypothesis testing, where it gives you a claim, gives you an observation in the form of a sample, and it's going to ask you to make a conclusion about this claim. And so you're going to go through all these steps of hypothesis testing that we talked about. Identifying HO and H1, assuming that HO is true, visualize the distribution, compare z-test to z-critical, determine whether the observation is in the body or the tail, and then reach one of these two conclusions. Either you fail to reject HO, or you fail to accept H1, or you reject HO and you accept H1. So only one of these two classes of conclusions is made. So after you reach one of these two conclusions, your homework is going to ask you for one or more of those steps in hypothesis testing. There's another question your homework could ask you, which is, it asks you to find the p-value. So this is a very important idea that in today's class we don't have time to go over. But in tomorrow's class, in the next class, we'll spend a lot of time talking about what it means to be the p-value. So for now, on the homework, start the homework, but there's going to be questions that ask you for the p-value, so you can just ignore those for now. So the homework won't be due immediately tomorrow, but start doing the homework. And then any questions about the p-value, you can not have to worry about until we talk about it at the next class. Okay, any questions?